Thank you for coming, everyone. What I want to talk about today a little bit is parallel processing. And I mentioned for EM simulation, I'm actually going to talk about parallel processing for EM that is then used in circuit simulation. So I'll make that clear in a minute. My name is John Dunn. I'm a support engineer at AWR. And actually, before I go any further, my colleague Eileen asked me to remind you, on your seats is an invitation to the party tonight, social highlight of MTT. So drop by the booth if you're interested. It's going to go 7 to midnight, and it will be across the street. So over in the booth, she'll get you all set up. So why are we talking about parallel processing? Everyone has a vague idea what that is, right? It means parallel, things happening at the same time. Sounds faster, sounds great. It's kind of the first thing you think of when you want to speed something up. Quite frankly, a child thinks of that. Why don't we do a lot of things at the same time? The trouble is when I look around the community, and there is parallel processing, of course, there's a lot of confusion as to what it really means, and also some of the pitfalls, and that's what I just want to go through a little bit here, if you are new to it, so you're a little bit familiar with some of the issues. So let's get going. So as you walk around the show, you're going to see this guy, and he's going to tell you that his EM parallel processes, okay? And it's the world's greatest thing. What could be easier? It will run, obviously, if you have 15 computers, 15 times faster, and computers are cheap, and you wire them together, and you're done. And think life is great. So that's what I want to get into a little bit. First of all, what actually people don't really appreciate is there's more than one class of problem for parallel processing. So most of us think of that slide before where we have the huge problem. You're going to solve, well, for example, the last talk, you saw these very large arrays, or you're going to look at the radar cross-section of an F-22 airplane, some traditionally large problem. And that is, in this slide, what I call class 2, the big problem. And you've got to divide it up spatially somehow. Each different processor does a different part of it. We'll get to that in the second half of this talk. But what I want to emphasize is that most circuit designers in their everyday work are actually doing class 1 when they parallel process. And these are EM projects run in parallel that are small, okay? So maybe you've got a little discontinuity, a bend, a T across, a notch T-junction, a single spiral, 2 coupled spirals. Any individual simulation will not tax the EM simulator that much, but the problem is you got a lot of them. And that's what I call a class 1 problem. And that's what I'd like to start with. So the first thing to appreciate, if you haven't thought about it before, is there's 2 very different kinds of parallel problem. The next thing to appreciate is that parallel processing is actually largely a hardware problem, okay? By that I mean in class 1, as we're going to see, we essentially have these independent problems that you're going to send to independent processors, computers, and it's up to the hardware and the connection to figure it out, okay? Even in the super large problem of type 2 where you're breaking the thing up spatially, we're going to find out a lot of it has to do with how the computers talk to each other, and that's usually the bottleneck. So as hardware improves, parallel processing will improve. Let's look at how hardware is parallelized quickly. First of all, everyone knows now that computers have multiple cores. I don't think you can buy a single core chip anymore, at least not for a standard laptop. And those are essentially independent computers. And then the next step would be the cloud. Everyone is hearing about the cloud. Everyone's got the cloud. It will be used by all the software companies more and more. Various pieces of the job will be sent out to different machines. Notice there's two issues here. We have the processor or the computer and how it talks to its neighbors. The speed of the computer, the speed of the communication, okay? Two different things. In parallel processing, you don't go any faster than the slowest thing. That's the classic bottleneck, okay? When everyone is getting on the bus to go to the party, that person who is getting ready and dressing the last is holding it all up, okay? No one's going anywhere. So when we look at the cloud, the interconnect speed between the computers, if they have to talk to each other, is slow. And that will, unfortunately, drive it. Obviously, cores talk together faster. And as we move up in specialized technology, there are companies out there that make specialized hardware. For example, you've seen the FDTD codes use GPUs, graphic processing cards, faster communication between them, et cetera, more specialized. And then finally, ultimately, maybe some of you are at certain unnamed government organizations and happen to have a blue gene sitting there, and you're in great shape. But for the rest of us, you're either going to be on the cloud or using multiple cores. Okay, class 1 problems. Where do you see these things? The classic example is you're building an EM database, okay? I've got a spiral. I want an EM database of several different turns, metal thicknesses, et cetera, diameters. And you build this up by running a number of simulations. The point being they're all independent of one another. You ship them out to different processors. They never have to talk to each other. They come back, you have your database, you're done. What could be easier, okay? And again, the key point is they're totally independent and they're relatively small. Other places where you're going to see this, besides sweeping the shape, is frequency, right? You'll send the exact same thing out at different frequencies, etc. And then finally, once you have these EM models, people will use them for tuning. They interpolate between the values with a tuner, or, of course, optimization. Now, when you look at these type 1 problems, if you talk to a mathematician, that's a mathematician there on the right. Mathematicians are polite people. They use the word trivial, okay? If you ever talk to a mathematician, they'll say the problem is trivial. That's math speak for a monkey could do this, okay? Which is you, all right? Or, in my case, the software developer, me. And in principle, a monkey could do it, but the problem is the mathematician is not throwing this into a circuit simulator, okay? That's the big difference. So let's look at the issues with the circuit simulator. Okay. So we're firing this off on all these cores. It's different computer, this type 1 parallel problem. And we've got 3 issues that we need to deal with. First of all, the key here is all the problems are independent. So you solve at 1 gigahertz, you solve at 2, you solve at 3, don't need to know about each other, life is good. Well, what happens when you run into things like optimization? Okay, so the next step in the optimizer depends on the previous solve. So how do you do several solves at the same time if they depend on the previous result? That's a problem. So there's one to deal with. Here's another one, advanced. Everybody now in EM has advanced frequency sweeping, called different names, whole bunch of frequencies, you want 1,000 of them. You don't simulate at 1,000 frequencies, you simulate at a few frequencies, carefully chosen, and it approximates all of them. The problem is to figure out which frequencies to simulate, the carefully chosen ones, I have to have the previous approximation. So how do I do this all at the same time independently? Another one for the software to develop, worry about, okay? As you get another problem that the mathematician doesn't have or the pure EM person doesn't have that we have to deal with in circuit simulators is this. You're firing off all these EM jobs and the results come back, and what are you going to do with them? You're going to use them in a circuit, right? And the circuit then, your amplifier, whatever it is going to simulate using those results. okay? We certainly have the capability in our software, other companies have this capability, that you can go out and fire these jobs off on different machines. Our new version of the software will allow you to have several different computers and fire them off, if you have enough licenses, of course. But here's the problem. So there's your circuit on the left, your circuit schematic, okay? And in that schematic, the layout of it, you're going to run an EM simulation. So some part of that circuit is being EM simulated. It runs off to the EM simulator somewhere, and it's simulating. Meanwhile, you, being a busy engineer, fire off a circuit simulation, a harmonic balance simulation, to see the power out of your amplifier. Does your harmonic balance simulation use the new EM result or not? Because the EM is completely independent of the harmonic balance. Now, the mathematician doesn't care, but you, the engineer, when you accidentally used an old EM result and didn't know it because the cloud's a little slow on the East Coast right now, just taped out a wrong chip and cost the company $250,000 for a bad chip run. So how do you handle that? So any software company, as you talk to the circuit simulation people, how do they handle this? Do they allow you to do that? Do they warn you? Do they not allow you to do it? It's an issue you really want to understand before you go firing these jobs off and then use them with other simulators, okay? It's not the problem of the EM simulator, it's the problem of the entire circuit simulation environment. How do we handle it? Quite frankly, the way we handle this problem is we don't allow you to do it. If you're going to ship a layout directly from a schematic like this, we don't allow you to simulate any other part of that thing until the EM finishes and comes back. It's just too dangerous to do it. That's our feeling, okay? Maybe we'll change that if some of you can convince us how you do it safely. But otherwise, you have no clue what results the EM and the HB and how it's all tied together, and you can get yourself in a total mess, okay? This is fairly obvious. If you're gonna, here's an example of a notch T. Most EM simulators have this, some kind of parameterization. You're making a user model here. This particular one has 3 variables, 8 values of the T, and the user environment has to support it. I don't have much more to say on that. Somehow you have to deal with the interpolation between the values. And of course, the parallelization is trivial. You send all 8 off at the same time, they're independent, but then how do you make the database? So again, these issues, it's not just the EM parallelization, it's how you work with it in the circuit environment to make it useful that's important. Okay? And again, I just covered that, so I think I will move on. And here we are again. Here's the model being used. You can move the 3 parameters, interpolate, optimization. These are all things that the circuit simulation people have to deal with. Not the EM, it's the circuit people. So just think, just because we have these, can I go back here? There we go. Just because we have this thing that a monkey could do, send the job to independent processors, what do you do with those when you get them back in the circuit simulation environment? That's the hard part. Not an EM problem, but an environment problem. Let's go to class 2. The big problem, right? You're going to do the F-22 aircraft. You're going to do the array of 10 gazillion elements, whatever that is. And you're going to do it on a gazillion computers. It's obviously going to speed up a gazillion times. And so if you can buy the computers and do it, you're good. What could go wrong? Okay. First of all, I'm sure most of you appreciate there are different kinds of EM simulators. There's the planar ones, sometimes called 2.5D, 3D planar. And there are the volumetric meshing ones, finite difference time domain, finite element method, finite integration method, all those little tetrahedra in space versus on the metal, you mesh it up. Ways to speed them up, including parallelization, and the issues are very different for the two different kinds of simulators. Let's take a look. I'm sure most of you know essentially how a planar simulator works. Let me give you the 30,000-foot view of it if you've never seen one. Here's a bend. You mesh it up. The current is approximated on each little mesh as a linear current. And if you solve for the current, you've solved the problem, you're done. The currents all talk to each other, just like in real life, by mutual inductance, capacitance, etc. And essentially what you do in this sort of simulator is you create a giant matrix, okay? A giant matrix. Now notice that that matrix is a full matrix. So for example, you see A1522, that's the talking between element 15 and 22. On the left, you have the excitation, which you know, it's 0 everywhere except where there's a port, it's 1. And on the right is how big the current is on the cells, which you don't know. AX equal B, solve the matrix, and you're done. Okay. How are we going to parallelize that, right? So that's what you got to do. How do you parallelize? Well, there are a couple ways we can do it. First of all, the good news with moment methods is they can speed them up a whole lot without parallelizing them at all, because they have fast solve techniques that never directly solve the matrix. They're iterative solvers. I don't have time to get into the details, but essentially because of mathematicians and then, engineers at companies implementing those algorithms, instead of that orange curve, n cubed, you can now go as n log n. Nothing to do with parallelization, it's just iterative matrix solvers. Does that make a big difference? Let's do a simple case, okay? Let's do 1,000 unknowns. And let's say 1,000 unknowns takes 10 seconds. Let's increase the mesh 10 times, 10,000 unknowns. N is 10, so now you would have 10 times bigger, n is 10, cubed is 1,000. You went from 10 seconds to 10,000 seconds, which is 3.5 hours, right? Try n log n. 10 log 10, log of 10, natural log 10 is too hard for me. What is it? I'm in marketing. 3.4? I don't know. 34 times more, 10 seconds to 340 seconds, 5 minutes. So 5 minutes versus 3.5 hours. That has nothing to do with parallelization. It is all through mathematicians figuring out these fast algorithms. That is probably the biggest speed up in moment methods in the last few years. Okay? But can you parallelize them? Yes, in many ways. One way that people do it, we do it at AWR, and it helps a lot, is basically when you look at filling the matrix and you look at doing the iterative solver, you're doing a lot of floating point operations, okay? So essentially, we go to Microsoft and they have libraries, math libraries, that take advantage of multiple cores. And we use them, okay? Has nothing to do with dividing up space or anything. You're just using, we can do all the FFTs at the same time, etc. Does it help? Sure. Now, for example, our planar solver, if you have a 4-core machine, you get about a 3.6 improvement. If you have an 8-core machine, you get about a 5.4. If you have a 16-core machine, you get about a 5.5. You seen a trend here? It goes up, but the efficiency goes down. The mathematicians at Microsoft are running out of steam, okay, because you can only play the game so long. Let's go to the finite element method. Finite element method, these are actually from particle accelerators. When we have a finite element code and we bought it from a company that they were doing, right? So a lot of particle accelerator examples. The different colors are different processors, different computers solving that part of the problem. What's the kicker here? The kicker is the regions have to talk to each other. In this type of code, you're meshing up space, all the little tets, but the ones on the boundaries have to talk to each other. All of a sudden, on the cloud, you got this guy here, this guy here, they have to talk. And remember everyone going to the party, waiting for the person getting dressed? You got to wait for the communication. So the problem is, you have to mesh it up the right way. It's highly dependent. And I'll just show you one quick result from this stuff. Look what happens in reality after a certain number of processors, it levels out and even goes down. Okay? So the secret is doing it correctly. It's still an open problem. Thank you very much. Hope you have a great show. Drop by our booth. We'll talk more if you're interested in this stuff. Thank you.